On the same origin of quantum physics and general relativity from Riemannian geometry and Planck scale formalism Part 1, Introduction and Key Findings. This new work represents an effort to unify quantum physics and general relativity through the lens of Riemannian geometry, focusing on energy tensors and curvature at the Planck scale. These two disciplines, which have shaped modern physics, remain fundamentally incompatible. By reformulating the key mathematical tools used to describe space-time and energy interactions, the authors offer a framework that addresses core questions in theoretical physics, such as the nature of black holes, quantum entanglement, and early cosmological structures. The foundational challenge that this paper seeks to address is the lack of a unified theory that reconciles quantum mechanics and general relativity. Currently, no universally accepted theory can explain the full range of physical observations. Quantum mechanics, which governs the smallest scales of the universe, subatomic particles, and general relativity, which governs large scales, planets, galaxies, operate in radically different ways. The mathematical structures of each theory appear incompatible. Quantum mechanics employs probabilistic wave functions to predict the behavior of particles, while general relativity relies on the deterministic curvature of spacetime to describe gravity. This work takes the approach of reformulating Riemannian geometry, specifically focusing on curvature and energy tensors using a formalism rooted in the Planck scale. The Planck scale is the smallest possible scale of measurement, where quantum effects of gravity become significant. At this scale, the constants of nature can be reduced to only two quantities, Planck length and Planck time. The authors claim that their equation can explain phenomena in both quantum electrodynamics and general relativity. For example, the equation can be transformed into both Dirac's equation for fermions and Maxwell's equations for electromagnetism. The central claim of the paper is that Einstein's field equation, EFE, from general relativity can be reformulated as a relativistic quantum mechanical equation by making it unitless on the Planck scale. In this context, the mass and charge of elementary particles are redefined as interactions between spacetime curvature and energy fields. Part 2, Mass Creation from Curvature and Black Hole Dynamics. One of the more provocative claims in the paper is that mass can be created from the curvature of spacetime. The relationship between curvature and mass is reciprocal, following the Onsager principle: mass creates curvature, and curvature creates mass. This is important for understanding the creation of mass in the early universe. As the universe expands, spacetime curvature decreases, but this curvature can generate mass and kinetic energy, momentum, in the process. This process of mass creation is mathematically described through the reformulation of Einstein's field equations and is shown to be consistent with quantum theory. The authors argue that the conversion of curvature into mass is essential for explaining the mass and behavior of fundamental particles such as quarks and neutrinos. The paper also addresses the issue of black hole singularities, a major challenge in modern theoretical physics. According to standard general relativity, a black hole's mass collapses to a single point of infinite density called a singularity. However, quantum mechanics suggests that singularities should not exist, as the laws of physics break down at such extreme points. In the paper, the authors propose that at the Planck scale, spacetime is entangled, preventing the collapse of a black hole into a singularity. Instead, black holes become white holes, which are the theoretical opposite of black holes. In this model, energy that collapses into a black hole eventually expands outward again through a white hole. The transition from black hole to white hole occurs because spacetime's quantum entanglement flips as mass collapses beyond the Planck scale. The authors suggest that black holes and white holes are entangled, allowing for the transfer of information and energy between them. This mechanism avoids information loss in black holes, addressing a key paradox in modern physics, the black hole information paradox. The paper further supports the conjecture that Einstein-Rosen bridges, wormholes, and quantum entanglement Einstein-Podolsky-Rosen or EPR entanglement, are physically equivalent. Part 3, Explanation of quark and neutrino masses. The paper also takes on the challenge of explaining the masses of quarks and neutrinos, fundamental particles within the standard model of particle physics. By applying the Planck scale equation to quarks and neutrinos, the authors calculate masses that are consistent with those predicted by the standard model. For instance, they calculate the mass of the electron and quarks, up and down, using their new model. The mass of quarks is predicted by dividing the electron's mass into fractional dimensions, corresponding to the internal structure of quarks. Using this method, they obtain mass values for the up quark, around 2 MeV, and the down quark, around 4.5 MeV, which are close to the values accepted in the standard model. Similarly, the masses of neutrinos, electron, muon, and tau neutrinos, are derived from the entangled curvature of spacetime. The results are consistent with the experimental constraints on neutrino mass, providing a novel quantum mechanical explanation for these particle masses. Part 4, ER equals EPR conjecture and quantum entanglement. One of the most exciting outcomes of the paper is its treatment of the ER equals EPR conjecture, a theory proposed by physicist Leonard Susskind and others, which suggests that quantum entanglement, EPR, and Einstein-Rosen bridges, ER, are two sides of the same coin. The authors support this conjecture with their Planck scale formalism, providing further evidence that quantum entanglement is deeply connected to gravitational phenomena such as black holes and wormholes. According to their model, entangled particles in different universes are connected via curvature interactions at the Planck scale. These interactions allow energy to be transferred between universes without violating the principles of quantum mechanics. Furthermore, the model suggests that singularities can be avoided by viewing the collapse of a black hole as the creation of a white hole in another universe, allowing for the continuous transfer of energy and information. This would imply that our universe could be one in a series of entangled universes, each connected by quantum and gravitational phenomena. Part 5, Cosmological implications, gravitational waves and the big ring structure. The authors apply their unified equation to cosmology, predicting gravitational waves and other cosmological phenomena. Gravitational waves, ripples in the fabric of spacetime, have been detected by observatories such as LIGO and Nanograv. The paper's equation predicts a gravitational wave background that is consistent with observations, and it explains how these waves propagate through entangled spacetime. The equation also sheds light on the formation of ultra-large structures in the universe, such as the Big Ring and the giant arc. These structures challenge the cosmological principle, which holds that the universe is homogeneous and isotropic on large scales. The authors suggest that these structures can be explained by the harmonic oscillation of the universe, governed by the lambda curvature. The oscillation of spacetime at the largest scales can lead to the formation of large-scale structures that violate the cosmological principle but are consistent with the new model. Part 6, Planck scale formalism and quantum gravity. The authors explore how their equation addresses the long-standing question of quantum gravity. At the Planck scale, quantum effects become significant for gravity, but current theories fail to explain how gravity operates on these scales. The paper's reformulation of the Einstein field equations allows them to incorporate quantum effects into gravity by making the equation covariant in spacetime and unitless on the Planck scale. This formulation leads to a new understanding of how spacetime curvature interacts with energy and mass at the smallest scales. The equation predicts that spacetime at the Planck scale is entangled, and this entanglement prevents singularities from forming in black holes. Instead, black holes and white holes become a means for transferring energy between different regions of spacetime, further supporting the ER equals EPR conjecture. Part 7, Concluding remarks and implications from Riemannian geometry. The paper presents a breakthrough by proving that Einstein's field equations, EFE, can be equated with quantum mechanics, particularly in the context of the Planck scale. This achievement is grounded in the principle that the equation governing quantum mechanics and general relativity must be unitless at the Planck scale, which resolves many inconsistencies between the two. By employing this formalism, the paper offers new ways to understand mass creation, black hole dynamics, and quantum gravity. It suggests that mass can arise from spacetime curvature, and it offers explanations for the masses of quarks and neutrinos, consistent with the Standard Model. Furthermore, the notion that black holes can become white holes via quantum entanglement opens a new realm of possibilities for avoiding singularities and conserving information in black hole collapse, providing a resolution to the information paradox. The ER equals EPR conjecture, supported by this framework, points to a deeper connection between quantum entanglement and gravitational phenomena such as black holes and wormholes. This work also predicts cosmological structures and gravitational waves consistent with current observations, challenging traditional views on the homogeneity of the universe and opening new pathways to understanding its large-scale structure. In summary, the paper provides a promising framework that unifies quantum mechanics and general relativity. It bridges key gaps in theoretical physics, from the behavior of fundamental particles to the dynamics of black holes and the large-scale structure of the universe.